This screencast is going to focus on the acid-base properties of salt solutions. This is something you were introduced to in first year chemistry, and it's one of those things that you can actually make correct predictions based on wrong chemistry. So we kind of went through where conjugates come from, and we talked about the fact that if you have a strong acid or a strong base, then its conjugate acid or conjugate base is not going to be very good at its job. And that's why we have the one directional arrow when we have strong acids or bases. We also learned in first year chemistry the general reaction that an acid plus a base makes a salt plus water. It's, in a sense, a double displacement reaction. But when we look at that, we kind of think of acid plus a base is always going to be neutral. And we saw that that wasn't always the case because it depends on how strong this acid is, and it depends on how strong this base is. Now, if it's a strong acid and a strong base, it'll certainly make a neutral solution. If it's a weak acid and a weak base, it'll usually make a neutral solution. But if one of those is strong and one is weak, then the salt will actually have the power to make an acidic or basic solution, so therefore it wouldn't be neutral. So we kind of go through each individual cation and anion, and we talk about where it came from. So when we look at something like NaCl, right? Na is Na plus, and Cl is Cl minus. And so we know that that salt came from the base and it came from the acid. So you can look and say, okay, well the cation from the salt comes from the base, which in this case would be NaOH. And the Cl minus comes from the acid, which in this case would be HCl. And then if we classify each of those as strong or weak, then we'll be able to predict, will the salt solution be acidic, basic, or neutral? So if I think about NaOH, that's a strong base, so Na plus really has no affinity to pick up a proton. And then if I look at HCl, that's a strong acid, so Cl minus has no affinity to do that either. So your solution of NaCl would be neutral because there's no hydrolysis going on. So, and that's this example right up to the side. So in order to know if a salt solution is going to be acidic, basic, or neutral, you can kind of look at common sense, but it's an example where common sense gets you to the right answer without the right chemistry. So this question says, if you mix a weak acid, so you think weak little acid, with a strong base, what do you think the pH of the solution will be? And basic is usually what students come to because they think, oh, this strong base is going to dominate that weak acid, when really there's a lot more going on. So if we look at this first salt, sodium nitrite, where did the, or is that asked, what base did the sodium come from? So that would be NaOH. And is that weak or strong? And we know it's on our list of strong bases. And then what acid did nitrite come from? That would be HNO2, and that is a weak acid. So even though we sit there and we predict strong base, weak little acid, so it should be basic, that's actually not why. It's actually because of this NO2 minus why this thing is going to be acidic, basic, or neutral, and in this case basic. So this little formula right here is kind of hidden, and every year I mean to make a bigger deal of it because it really is a big deal, and we'll be using it in some of these example problems. But when we talk about Kw, we know that the product of the H plus concentration times the OH minus concentration is equal to this constant Kw, and there's a cool relationship between Ka and Kb. So like if you were to know the Ka for this acid, which it's a weak acid, so it would have a Ka, we know that NO2 minus is the conjugate base for that acid. So if you wanted to know what the Kb was, you could use this equation over here and say it's just equal to Kw over Ka. And where would that Ka come from? It would be the Ka of that acid. So we're going to use that over and over again, so it's really an important formula. And if you'd like to look at the derivation, it is in your textbook. Alright, so we're going to look at this first one, sodium azide, sometimes used to kill bacteria in water. So they want you to calculate the pH of a 0.01 molar solution of NaN3. And then they give you the Ka for hydrozoic acid. All right, so if you're looking at this and you're like, they've given me a salt and they want me to know the pH of it, I want your brain to go to salt hydrolysis. And that may sound scary, but all that means is that one of the ions from the salt is going to hydrolyze. And hydrolyze might sound scary, but all that means is to interact with water. So what you have to do when you're given a salt is figure out, well, which one's going to hydrolyze? So it's what we just did up here. We say, okay, where did the Na plus come from, right? Because this is made up of Na plus and N3 minus. So kind of a weird triatomic ion there. So we know that Na plus comes from NaOH. And then we think about N3 minus, well, if that came from the base, then this guy had to come from the acid. So we're going to pop an H on it. And so that would be HN3. So this is hydrozoic acid. And if you didn't know that, then you can think, oh, well, look, they gave me a Ka, so obviously this thing has something to do with hydrozoic acid. So let's back up a little bit. If we've got a strong base and we're mixing it with a weak acid, your prediction for pH would probably be basic. And that is absolutely right. But does it have anything to do with the strong base? The answer is no. It has to do with the weak acid, and more specifically, the conjugate of that weak acid. So this conjugate is going to undergo salt hydrolysis. Okay? So I'm going to erase this just so I have a little bit more room. So N3 minus is going to interact with water. And so then you look at that and say, okay, well, what can he do? He doesn't have a proton to give. He's a conjugate base of a weak acid, so he's going to take on an H and make HN3. And then that H came from the water, so what's left? OH minus. The reaction writing is the most important part of this, guys. If you can't write the reaction, then you will be going kind of blindly into this, not knowing like what the next step is. So part of what we're going to do is we're going to practice and make sure we're really good at writing these reactions out. Because as soon as you have a reaction, you have a starting concentration, we've got a K that we're not going to use directly, but we'll talk about that in a minute. You can certainly set up an ice table, and that kind of gets you rolling in the problem. All right, so let's go back to ionic compounds. If this is NaN3, it's got a 1A element, so we know it's soluble. So NaN3 in solution is going to break up into Na plus and N3 minus, right? So the coefficients are 1 to 1. So if this solution is 0.01 molar, then I know the concentration of that, right? It's 1 to 1. So I know that my starting concentration of this is 0.010. And both of these are 0. I'm sorry, guys, I had a minus there, and I should not have a minus. If it was negative, it gains a proton, it should be neutral. All right, so we think about this equilibrium. We know it's going to shift right, so let's do minus x, and plus x. So we have 0.010 minus x, and x. Now, here is the most common mistake students make. They get this pretty ice table, they see a K up here, and they're like, oh, I'm going to use that K. Here's what you have to check. This is a Ka, and we look at this equilibrium, and is this acidic? Absolutely not. So we don't need a Ka, we need a Kb. Okay, we've got the Ka for the acid. How do you think we get the Kb for the N3 minus? Well, remember this relationship right here? The product of the Ka and the Kb equal Kw. What is Kw? It's a constant. So the Kb for this is Kw over Ka. So to get Kb, I'm going to do 1 times 10 to the negative 14th over the 1.9 times 10 to the negative 5th. That's the chemistry of it, right? Knowing that you have to solve for that Kb. So that Kb comes out to 5.3 times 10 to the negative 10. Based on that K, it's super, super tiny. I should be able to assume that this is basically equal to 0.010. So then I set up my x squared over 0.010 equals my K, 5.3 times 10 to the negative 10. So when I get that x, it's not going to be an H plus, it's going to be an OH minus. And so OH minus equals 2.3 times 10 to the negative 6. So if I negative log that, which kind of becomes our habit, right? We negative log, we get an answer. That negative log is a POH. And so that negative log is 5.64. Go back to your prediction. We said that this thing should be basic to begin with. Even if you thought that that was a pH, you see 5.64 and you know, oops, that's for an acid. So now I need to subtract, I'll go up here, 14 minus 5.64, and my pH is 8.36. So indeed it is basic, not hugely basic, but just the hydrolysis of this N3 minus causes it to be a basic solution. Okay? We're going to do one more together, and then we've got some examples of salts that we may do together in class based on how this goes. All right, so for acidic solutions, all right, we're given this ethyl ammonium chloride, which looks pretty scary, I know. And if you look at it, you're given a 0.25 molar solution of it. So I want you to think of it as this cation with this anion. So this thing is going to break up into C2H5NH3 plus Cl minus. Okay, so that's what we've got to be able to do. We've got to take whatever scary thing they give to us and break it up into a cation and an anion. Now look, the Cl minus comes from HCl. So is it going to hydrolyze? Absolutely not, because it came from a strong. But this guy can hydrolyze. So the most important part is writing this solution out. So C2H5NH3 plus, and hydrolyze just means interacts with water. So it's going to interact with water. Okay, if that was the conjugate base, then this is a conjugate acid. And what do acids do? Acids give up their H's, so that H is going to be transferred to the water and make H3O plus. And then what will be left? The C2H5NH2 neutral. Okay, so they're telling me that the starting concentration of this salt is 0.25 molar. Since it's 1 to 1, what's the concentration of both of these ions? Well, it's equal to that. It's 0.25 molar. So these are both 0 to begin with. I go up by x, minus x. So this is 0.25 minus x, and x. Now, I didn't give you the K in the problem. They would give you a KB for this guy, which is equal to 5.6 times 10 to the negative 4th. Okay, and you come and you look at this reaction, and hopefully you say, uh-oh, I'm producing a hydronium, so I can't use a KB. So I convert this to a Ka by doing Kw over Kb, and the Ka comes out to 1.8 times 10 to the negative 11th. We should be able to assume that the 0.25 minus x is basically 0.25. So I set it up and I say 1.8 times 10 to the negative 11th is equal to my products, which is x squared, over my reactants, and I'm going to assume that it's pretty much unchanged. So when I get my x, it's equal to the H plus concentration, which is 2.1 times 10 to the negative 6. So the pH comes out to 5.68. And before you move on, stop and ask yourself, it came from a strong acid and a weak base. The prediction was it would be acidic. And it's not acidic because of that Cl minus, it's acidic because of the hydrolysis of this guy. So is that an acidic pH? And it's yes, and so then you can move on. Okay? So this kind of gives you an overview of the equilibrium. It's really not the equilibrium calculations that are hard, guys, because it's the same thing we've been doing, right? What's difficult or challenging is knowing, 1, what is the salt breaking up into, and 2, where did those ions come from? 3, figuring out, do those ions hydrolyze? Because if they do hydrolyze, then that will impact pH, okay? So you've got some homework problems on these. I've summarized for you at the very bottom, what happens. This isn't really anything new. It's the same stuff we saw in first year chemistry. The only difference is this. If it's a weak, we kind of said, oh, it's pretty much going to be neutral. You can actually compare it. College Board isn't super stressed about that part. They really focus on giving you a strong with a weak and making sure you understand the hydrolysis. So try these homework problems, see how they go, and then we'll go over these together as a class when we get back from our snow day. Thanks, guys.